Hello everybody, how is it going? Welcome to GET1028, GEX1014 Logic. And this is going to be the first lecture, just a little introduction, just a little bit of me talking about why I like logic. So let's get into it. So I think it's good when you start anything to ask, why am I doing this? And particularly because I'm a philosopher, I'm in the philosophy department, I should be able to give you some good motivating reasons as to why you should take this course. So here's my main aim for the lecture. I want to give you some motivating reasons to take the course and find it interesting. And I'll do this in these three little sections. So first up, we'll talk about what logic is, right? What are the foundational ideas or characterizations of logic. I'll then talk a little bit about the notion of argument. This will be very, very important for thinking about logic and key for what we'll do a lot in the course. And then I'll give you a kind of little smorgasbord of why logic's important to me, why I find logic so interesting, and why you might find it interesting too. Okay, cool. So let's start out. You can't know whether something's worth doing without knowing roughly what it is. So here's our first opening question. What is logic, right? What am I talking about when I say logic? Okay, and here's a very rough and kind of controversial characterization, right? This is something that happens a lot whenever you try and characterize anything of any interest. You run into problems. Often things are going to be rough and controversial, but this I think is a nice way to get going. Okay, so logic is the study of good inference or good inferences. You can argue about whether that's a good characterization, but for the purposes of this course, that's going to be a nice starting point. Now, you might worry that this is not a tremendously informative characterization, as the notion of inference, right, let alone what's good, is also going to be really, really difficult to characterize. But I think you do get some progress here. So we're interested in how some sort of good-making feature of a statement, and in that case, this is going to be truth. Something you can do if you go beyond this course is look at cases where you get different kinds of preservation between statements. Gets communicated from some statements are premises to others are conclusion. So this is going to be the kind of focus for this course. We're thinking about statements, and these can be true or false, and then we're going to communicate that truth between the statements we start with and a particular conclusion. Now, you might think, okay, this is just a very simplistic notion of inference, right? We do this all the time. We talk about what's true, or we make arguments, and we talk about what follows from those claims we started out with. It is simplistic, right? And this is one of the lessons we've learned from logic, and one of the reasons I find it interesting is that a very simple idea, when you get it just right, can actually be very, very powerful. And this is something we'll see later on in the course. And I'll talk a little bit, I'll give you a little peek into this later in this first lecture. Okay, so if you notice on the last slide, I talked about premises, right, and a conclusion. First claims are our premises, and the conclusions are our last statement. This is highly suggestive of the idea that we're concerning ourselves with arguments, and that is what we're going to do in the course, right? We're going to be primarily concerned with arguments, how we can formalize those, and then what we learn from those formalizations. So what is an argument? Well, we have a conclusion, and then we have support from some different premises, okay? The conclusion is inferred from the premises. Okay, there's a few different kinds of argument we can consider. So here's one. Inductive arguments take many observations or instances of a phenomenon to make a generalization. So here's an example. Every dog we've ever seen needs oxygen to survive, right? I've got dog A, I've got dog B, dog C, dog D, right? Loads of dogs, each one of them, every time I look at a dog, it turns out needs oxygen to survive. So we generalize from this large number of instances to the claim that all dogs need oxygen to survive. Okay. Now, this is commonly called an inductive argument. I'm taking a large number of examples and I'm generalizing from that to a conclusion. And in particular, it's what's called ampliative. Okay. Now, why is it? What does this mean? This means that the conclusion kind of contains more information than the premises. Okay. I haven't gone around and checked every single dog in the whole universe, but I have gone and checked a small number, and claiming that every dog needs oxygen to survive, not just A, B, C, and D, or all the ones I've actually observed, goes substantially beyond what's contained in the premises. So this kind of inductive reasoning, this is very common, for instance, in a lot of scientific work. You generalize from a large number of instances to try and make a general claim. Okay, similar remarks apply to what's sometimes called abductive inference, or sometimes inference to the best explanation. So here's an example of this. I noticed that you have blood on your hands. Let's say there's been a murder, okay? I noticed you have blood on your hands, your fingerprints were on the knife, and you have no good alibi. And from this, I conclude that you were the murderer, okay? Now, what am I doing here? I'm taking this collection, right, of observations, right? And I'm saying, look, a really good explanation of these observations is that you're in fact the murderer, okay? So this is maybe a little different from the inductive case I gave you on the last slide, because it's not like I've gone around observing loads of murders, right? And generalized from that all murders must be of a certain kind. What I'm doing is I'm putting together the different pieces of data, right? And I'm saying, look, the best explanation, all other things considered, is that you are, in fact, the murderer, okay? There's a bit of disagreement on the nomenclature here between inductive and abductive. Some people, for instance, could consider induction to be a sort of form of abductive inference. Let's not get into those details. The point is, there are loads of different kinds of arguments for conclusions, and some of these are going to be ampliative, like induction and abduction. Okay, so that's inductive and abductive inference. And they can be really, really good. They're really useful. We use them all the time. But what we're really going to focus on in this course is what I'll call deductive inference. Okay? These kinds of arguments are non-ampliative and intended to guarantee the truth of the conclusion, assuming that the premises are true. So think of passing truth from the premises to the conclusion. It's not the case that, as with the inductive and the abductive one, that the kind of amount of truth or information can grow as you move between your premises and your conclusion. Really, this is more constricted. We're just passing the truth downwards. Okay. Now, it's a little bit more restricted in one sense, but in another sense, it gives you a bit more security. So here's a kind of natural example of a deductive argument. Okay. So if I'm working at a computer right now, then I'm using electricity. I am working at a computer right now, so I'm using electricity, right? It's a really, really secure kind of argument, right? If I'm working at a computer right now, then I'm using electricity. That seems like a true premise. I am working at a computer right now. That's true, right? And so by premise 1 and premise 2, I can pass the truth of these two premises, right, to the conclusion that I'm using electricity by inferring from the conditional premise 1 and this antecedent of the conditional, as we call it, premise 2, to the claim that I'm using electricity. Okay, so as a convention, we'll use this kind of form a lot, where we write the premises first and then we have the conclusion at the end. But this needn't be the case, and this is important for when we come to analyze natural language arguments. So consider the following argument. I must be using electricity. After all, I'm working at a computer right now, and if I'm working at a computer, then I'm using electricity. Okay, this is basically this argument, right? But packed into a form in which the conclusion comes first. Yeah. So one thing we want to do, particularly when we're trying to extract the logical form of natural language arguments, this is something we'll do a bit later in the course. I want to be really aware of where the conclusion is and where the premises are and how they're all related together. This isn't always a trivial thing to figure out, and we'll have some exercises that test you on exactly that kind of thing. Okay, good. So we've got this idea of inductive inferences and abductive inferences, the ampliative kinds, and then the ones we want to focus on, right? The really constrained ones where truth gets passed from premises to conclusion. These can still go wrong, however. They're not, it's not the case that if you've attempted to make a deductive argument, you're always going to end up with a true conclusion. And there's two corresponding virtues associated with deductive arguments that will be really important for us to look at. Okay, here's the first one. We're going to say that an argument is valid if and only if it is impossible for all the premises to be true and for the conclusion to be false. Okay, so let's have a think about this. So our electricity example from earlier was valid. If I'm working at a computer, then I'm using electricity, and I'm working at a computer. Those two together entail that I must be using electricity. But let's consider this little tweak to those to that argument. First premise: if I'm working at a computer right now, then I'm using electricity. Let's keep that the same. But now let's have the second premise be I'm using electricity rather than I'm working at a computer. And let's suppose I try and conclude from that I'm working at a computer. Okay. So is this argument valid? So pause the video now if you want to have a little think about that. Okay, so it's not valid, and it's a bad attempt at a deductive argument. Okay. The premises can be true and the conclusion false. Okay, so suppose I'm using an electric coffee grinder, right? So there, it's still true that if I'm working at a computer right now, then I'm using electricity. I am using electricity, right? But I'm not working at a computer. The reason I'm using electricity is that I'm using an electric coffee grinder. Okay. So what we have there is an example, right, in which the premises are both true, right, but the conclusion's false. So this is not valid. It can be the case that the premises are true and the conclusion's false. Okay, I'm going to just present a little puzzle to you to go away and think about. I won't give you the answer to this, but we will talk about this kind of thing. What about the validity of the following argument? So, premise 1, I'm not working at a computer right now. Premise 2, I am working at a computer right now. Conclusion, I make the best laksa in Singapore, but Neil makes the best laksa in Singapore. Okay, this argument seems kind of bad, right? However, just think about what the definition of validity is. That the premises, it's impossible for the premises to all be true and the conclusion false. Just go away and think a bit about how that definition interacts with this kind of example. Okay, so we'll talk a little bit about that later, but that's just a puzzle for you to go home and think about. Okay, let's move on to our second kind of virtue. Let's suppose we have a valid argument. Even a valid argument can be problematic, however. Okay, so let's go back to our previous example. If I'm working at a computer right now, then I'm using electricity. I'm working at a computer right now, so I'm using electricity. Perfectly valid, right? But let's suppose we're in a situation in which I am in fact grinding coffee, but I'm using a manual coffee grinder. And let's suppose I'm otherwise not using electricity. Let's suppose I've gone to a little hut in the mountains or something like that, and I'm not using electricity at all. I'm just grinding coffee on a manual coffee grinder. Okay, this argument remains valid, but premise 2 is false, right? I'm not working at a computer right now. Right? Okay, argument remains valid, but premise 2 and the conclusion are false. Okay, so the important thing about validity is it's a very nice property of arguments, but it doesn't guarantee that all the premises are true, right? So it doesn't guarantee you that the conclusion is also true merely by validity alone. We're going to need a stronger good-making feature. And we're going to say that an argument is sound if and only if it is valid and all the premises are true. So not only does the truth of the premises guarantee the truth of the conclusion, but also those premises are true. Right? That's a stronger property than validity. Okay, great. So we've got these notions of validity and soundness. These are going to be really key for the purposes of this course. Here's some other really important notions that I'll let you think about in your own time. And we can discuss a bit around the lecture and tutorials and stuff. Okay. Sentences are jointly consistent if and only if it's possible for them all to be true together. So now I might have just a bunch of sentences and I want to know, could these all be true at the same time, right? Have a bit of a think about how that definition might interrelate with the definition of validity. Okay, the sentence is necessarily true if it cannot be false, right? So there's no way that particular sentence could be false. And a sentence is necessarily false if it can't be true, right? This is kind of the opposite of necessary truth. And finally, a sentence is contingent if and only if it could be true or it could be false. Okay, so you have the idea that it doesn't have to have one particular truth value. I'll let you think about that a bit on your own time. As I said, we'll discuss this a bit in tutorials. Okay, cool. And what we're going to do a lot in this course is we're going to see formal ways of modeling these ideas. We'll talk a bit about this a bit with respect to validity, but we'll also talk about these notions and we'll add a bit more kind of formal rigor to these as we go through the course. Okay, great. So I've given you just kind of very most introductory start to the course. I want to now talk to you a bit about why logic is important to me. Okay, so here's a question. Okay, you started off by saying you're going to give me some motivating reasons to take the course, but why should I care? You've just given me this notion of truth preservation and then some definitions, and this is all really unclear to me as why I should be interested in this field. Okay, here's a few things that we should start by saying. Okay, there is a reason why I titled this lecture "Why I Like Logic" rather than "Why is Logic Important?" Okay, and the reason for that is it's such a difficult question to really answer why logic is important. But I can tell you why I like logic. So here's some reasons I've settled for as to why I like logic and why it's important to me. Okay, these are things that I learned kind of after I'd done my introductory logic courses, but really brought it home to me how kind of cool a subject logic is. Okay, so from everything I say from now on, everything that came before, we'll talk a bit more about in class, right? And well, in particular, you might get some exam questions on that. But what I say now is going substantially beyond what we'll cover in the course. This is more kind of for your interest. Okay, so first, logic appears all over the place, okay? Here's a very important idea. In logic, a lot of the time, we're interested in conveying information, in our case, truth, from one collection of statements to another. And in particular, when you do that, it's also important to analyze what I can express using different resources, right? So anybody who speaks more than one language will know that even for natural language, there's things that are more easily expressed in one language compared to another. This is something that pops up in logic all the time. There are things that you can express in one language with one set of resources that you can't express in another. So this ability to analyze both conveying information and what can be expressed is really, really important in a lot of areas. So here's some. I mean, it's really clearly important in philosophy. In almost every area of philosophy, you'll have some vocabulary that you want to learn to employ. From mathematics to ethics, almost wherever you go in philosophy, you're going to be concerned with arguments and what you need to express the claims of your discipline. This is this is a place where logic is going to be really, really useful. Pops up a lot in linguistics, right? Linguists are studying a lot of the time how you can model particular ways of humans expressing themselves, right? Logic's very useful for that kind of endeavor. Mathematics, you want to know what you need to do to express a mathematical claim. Computer science, you're very concerned with how information gets moved around a particular system. Logic gets very important. I could go on. Anytime you have a notion of argument and information transfer, English literature, history, right? You're gonna be able to think about what is the underlying logic of this discipline. Okay, so pops up all over the place, and for that reason, it's pretty interesting. I think I can say a few things that are more specific rather than the general, logic is everywhere kind of comment. There's some really interesting results that come out of logic that are not just kind of interesting from the point of view of the logic involved, but I think are really philosophically important for how we think about the world. Okay. So this is a kind of double warning. What I'm going to say now is going well outside the material for the course. But what is interesting is what you're going to do in this course is learn the foundational building blocks that enable us to prove these results. Okay. So they're kind of in the picture of what you're doing in this course, even if you're not going to learn about, how to prove some of these results directly. And I hope that's going to be helpful to give you a sense of what's out there. Okay. So here's a bit of setup. Part of what you're going to learn to do, we're going to talk a lot about informal concepts and how they get employed, the informal concepts of validity, for instance, that I've already given you. But we're also going to learn how to take some of those informal concepts and make them symbolic. And this will let us deal with them with a bit more precision. Okay, this is a really powerful tool. Okay, perhaps might not seem that powerful when you start doing it, but what's really important is once you can symbolize things, you can use computers to check your work, right? And this has, really big payoffs. So think about how computers revolutionized arithmetical calculation, right? So you want to do long division or something like that, right? Real pain to do by hand. Absolutely trivial, can be done in seconds if you have access to a reasonably powerful computer. Not even that powerful for basic arithmetic. So what logic allows you to do is think about, how you can do addition and things like that trivially on a calculator, right? You can do similar things with reasoning as long as you can get them into a suitable formal structure. And we've had some real success in doing very long and complicated reasoning calculations using computers. So a couple of examples here. The Appel-Harkin proof of the four-color theorem. This depended on taking some huge number of maps and coloring them, right? Hales's proof of the Kepler conjecture. This is something about how you can pack spheres together. And these were proved by, taking particular kinds of reasoning, formalizing them, and letting a computer run on them. And this just would not have been possible without tools of logic. Okay. And, given successes like that, it's very natural to ask yourself, can we just delegate all our reasoning to computers? This is a really natural question to ask. And if you do ask that, you'll be in very good company. So this is Leibniz, one of the kind of our intellectual ancestors for computation. Tremendously talented polymath, very active in the 17th century. Famous quotation from him: when there are disputes among persons, we can simply say, let us calculate without further ado and see who is right. So, what Leibniz is dreaming of here is a world in which everything has been made so precise, right, that you can simply delegate your reasoning to a machine, right? And that will just do the calculations and check which of two people who are disagreeing is correct. Okay, but this is not going to be universally possible. And part of the reason we know this is by advances in logic over the last 150 years. So the kind of moral here is that logic is really tremendously powerful, but by studying logic, you can see some real limitations to the things that we can do. Okay, here's some interesting limitations. Question: is every function computable? So what does that mean? Let's suppose you just have something that's taking objects and mapping them to other objects, right? So this could be like the function +1 or whatever, or it could be, the function that takes every person to their biological mother, let's say, right? This is a kind of mapping, right? You might wonder, is it the case that anytime I have a mapping like that, I can always just get a computer to run it? Answer: no. And this is something called the halting problem. There are functions from the natural numbers, that just means 0, 1, 2, 3, and so on, to the natural numbers that are not computable. You're not going to be able to compute every function. The way you do this is you formalize, you show there's a relationship between computers and some kinds of formal theories. In fact, some formal theories we'll discuss in the course. Here's another question. Okay, this is called the Entscheidungsproblem, or decision problem in English. Suppose I write down some theory, right? I just write down a list of sentences, A, B, C, and so on. And this will in fact apply to some of the systems we'll learn about in the course. Obviously, we won't go through this complicated stuff, but we will learn about the underlying systems. Can I always tell a computer what can and cannot be proved using that theory? So can I always just get a computer to look at these sentences I've written down and say, oh yeah, D does follow from that for some other sentence D, or D doesn't follow from that, right? Might put no, right? And yes. Okay. Can you do that? It'd be lovely if we could. No, you can't. This is also via the halting problem that I mentioned on the previous slide. You can't always answer computationally what are and aren't the consequences of theory. So this is really, really interesting, these two results, right? So you might, whatever field you're in, be like, oh, can I always formalize what I want to do and always get like a definitive yes or no answer? And could I just feed that into a computer? No, right? And we've learned that in the last 150 years. Last one. If I write down a theory and I need some nice properties in the background that I'm not going to mention here, it's a bit complicated, but it's basically whether you can do math within the theory, in particular arithmetic. Is it possible to show using that theory that you could never produce a contradiction? You'd never run into a necessary falsehood, if you will. Answer: something called the second incompleteness theorem. No, you can never show this internally if the theory has those nice properties. And again, it took us formalizing the relevant notions to be able to see this. Okay, that was all very, very far beyond the course, that last few ideas. The core stuff I want you to remember from this little presentation I've given is just the notion of arguments, right? Different kinds of arguments, in particular, inductive arguments, abductive arguments, and deductive arguments, primarily focusing on distinguishing the deductive arguments from the non-deductive ones, and then the notion of validity and soundness, necessary truth, necessary falsehood, contingency. Those are the main things to take away. Don't worry too much about what I just talked about. That's kind of, if you're really interested, you can look those things up. Don't worry about those last examples, right? I think that's super interesting. You'll be learning the foundations that would let you go on to do that in the future if you wanted. But really, this is an introductory course in logic. Don't worry, I'm not going to go full math babble on you at any point in the course. You are not going to be examined on those examples. If you're really keen, look them up on YouTube or Wikipedia, or come talk to me about it once or a few weeks into the course. I'm always happy to talk to people. I hope that you've got a glimpse into the vast universe of what's out there. I really only mentioned a fragment of what I find especially interesting, but there's really a lot out there if you want to go look for it. I just think that when we're learning the basics, right, it's maybe nice to remember that you're starting to understand the foundations for this universe, right? Even if, we'll do a lot of things where we take a natural language sentence and we learn how to represent it in a formal system, right? Sometimes it can be a little frustrating and unclear why you're doing that, right? Useful for if you're into philosophy, you might wonder, what is the practical use of this? Well, the practical use is that it underlies a lot of other really interesting stuff. You're really just going to be learning the basics in this course. I think it's a really beautiful and puzzling world out there. And logic has, really great power, but like all good superpowers, it has some serious limitations too. And as you folks starting out in logic, you have a real opportunity here to go and think about what you make of those limitations. So I'm looking forward very much to the course. I'm looking forward to meeting you all in person. I'm going to leave you with Ada Lovelace, another one of our intellectual ancestors who contributed a lot to the foundations of logic and also computation as it happens. And she said, I never really am satisfied that I understand anything because understand it as well as I may, my comprehension can only be an infinitesimal fraction of all I want to understand. So a very nice little quotation there from Lovelace, and one that I think will inspire us as we go forward learning about logic. So looking forward to meeting everyone. Thank you very much for listening. See you soon. Bye.